Okay, so this will change somewhat. Homework 5 is due on Tuesday, October 3rd. It's already up on NU Online, and I've done the first two problems. The third problem, I haven't fully verified that there's no weird things about it, but I'm going to do that this afternoon, and if there's any changes, I'll let you know. Ignore that second thing about exam revisions. We'll talk about that after everyone has taken the exam. So a vapor power cycle is different from a gas power cycle in that the working fluid will be alternately condensed and evaporated. So when we talked about gas power cycles from Chapter 9, we're looking at something where the working fluid is treated as air. It's an ideal gas throughout the entire cycle. We have a turbine and a compressor. But in vapor power cycles, because we're alternating between a liquid and a vapor, we use instead a turbine and a pump. So the analysis is very similar, except for we now have a liquid as our working fluid rather than an ideal gas. So as you approach the analysis of vapor power cycles, it is most likely that you will be using tables exclusively rather than using the ideal gas equation to calculate property values. So in vapor power cycles, they're used in many cases to generate electricity. So steam generation of electricity is fairly common, particularly in the US. This is what the primary methodology for us to get electricity, even more especially in this part of the world. And the electricity is generated by burning a fuel of some sort, which acts as our heat source. So here in this part of the country, it's usually natural gas or coal. It can be nuclear as well, although there aren't any plants close here in West Virginia. So regardless of what heat source is used, the cycles are analyzed in the same way. So all we do with that heat source is we just treat it as a Q in, and we can analyze it just assuming that there's heat coming from some source that we don't necessarily need to know what we're burning or how we're burning it or anything like that, just that we are receiving heat. So the Carnot cycle is one that we're very familiar with. We've talked about it as this ideal cycle that's a reversible cycle, and it's easy to analyze because on a TS diagram we have a perfect square. So is it suitable for a vapor power cycle? And for those of you that were in class last semester, this PowerPoint should be fairly familiar. But if we look at the Carnot cycle and we try to imagine using it for a vapor power cycle, we have state 1 to 2, which is isothermal heat transfer, state 2 to 3, which would be isentropic expansion, state 3 to 4, which is another isothermal heat transfer operation, and then state 4 to 1, which is isentropic compression. So if we look at the Carnot cycle and we try to imagine operating under the dome, can we really do it with this particular process or this cycle? So if we look at this isothermal heat transfer from 1 to 2 and 3 to 4 on this diagram, so 1 to 2 and 3 to 4, it's supposed to be isothermal. That's easy to do when we're operating under the dome. So it looks like those stages, those phases could be complementary with the Carnot cycle. But states 2 to 3 and 4 to 1 involve isentropic expansion and isentropic compression. The expansion is not too difficult, but if we're dealing with a low quality at state 3, we're going to have interference with impingement upon our turbine blades. There's going to be some vapor-liquid mixture, which causes uneven rotation of the blades. We can have imbalances in the turbine, pitting, corrosion, a lot of other problems. So it's not really an ideal process. Similarly, from state 4 back to state 1, it's an isentropic compression process, which again is not easy to do in practice, because generally we use pumps to compress liquids and we use compressors to compress gases. So having some two-phase compressor or two-phase pump is a very expensive process. It's very difficult to moderate, and it's not really ideal for the situation of generating power because it requires a lot of power. So we can't use the Carnot vapor cycle operating under the dome. Let's look what happens if we try to operate above the dome, or where a portion of it is in the superheated region and a portion is in the subcooled region. So it fixes some of the problems. State 3 to 4 is still an isothermal heat rejection process, which is easy to do. State 2 to 3, we're going from a superheated vapor to a saturated vapor, which we can do in a turbine. But things get a little bit weird when we're trying to go from state 4 to state 1 because we're operating above the critical point temperature. And if you recall from the video last year, that anytime we're operating at, near, or above the critical point, phase change gets a little bit nefarious. So it goes suddenly from a liquid to a vapor without actually going through a phase change process. If that happens inside of a pump, that's a very bad thing. Cavitation occurs, we get something called dry lock, where you suddenly have this vapor within your pump that causes it to stop working correctly. So the Carnot cycle isn't really a good candidate below the dome or within the dome, and it's not a good candidate if we move it up above the dome. So we need to do something to this Carnot cycle to make it more, to have it be more amenable to the process which we want to have occur. So the Rankine cycle is the Carnot cycle modified to have more positive attributes when we're working with two-phase fluids. So if you notice on this diagram here, if it were the Carnot cycle, we would have this neat little rectangle, but instead with the Rankine cycle, we're superheating the vapor at state 3 well above the saturation point, and we're cooling from state 4 to 1 and condensing the liquid completely from a saturated vapor all the way down to a saturated liquid. That eliminates the problem of having two phases in our pump or our compressor. In this situation, we will use a pump because it will be liquid, and it also minimizes any chance of having significant liquid at the outlet of our turbine. So the Rankine vapor power cycle can be considered as the Carnot cycle modified to better fit the vapor power cycle model. So when we look at the vapor power cycle, in the ideal case, state 1 to 2 will be isentropic compression. So we're increasing the temperature of the fluid slightly. It's exaggerated on this diagram, but we're increasing the pressure sometimes significantly. In many cases, we're going from on the order of like 100 kilopascals to 5 megapascals up to the boiler pressure. So we operate at the edge of the dome, and by increasing the pressure, you'll notice that we're hopping pressure lines. So this is a line of constant pressure, and this is a line of constant pressure. And this goes back to, this provides a better explanation of why we use the temperature when we're looking up liquids, when we're making the compressed liquid approximation, rather than looking it up by pressure. Because we're looking at a significant pressure change here, but it's a pretty minimal temperature change. So when we're making that approximation, if we're going to look at the table in terms of pressure rather than temperature, we're going to have a very different value than we do if we look at temperature rather than pressure. So I hope that makes sense, but that's why when we make the compressed liquid approximation, we look it up at the temperature. So once we have compressed our liquid, we then add heat to it to evaporate it. And so it follows this line of constant pressure in the boiler. It starts out as a compressed liquid, and it ends up as a superheated vapor. So all of this heat that's added to the liquid is to induce a phase change, because we want steam from state 3 to state 4 running through our turbine. And that's what gives us a work output for our vapor power cycle. Then as it exits the turbine, it's either a saturated liquid vapor mixture or very close to being a saturated vapor, and then we condense it in the condenser back to state 1 to be pumped up back to the boiler again. Yes?
So when it goes to state 3,
yes,
it's the superheated vapor?
Yes. Yes.
So is that like as high? So is it like the more superheated? Does that mean it's like less moist?
Yeah. and a vapor that's very superheated is often called a dry vapor for that very reason, that there's less liquid that's about to condense in it. So even though it maybe contains the same quantity of water, it's in the vapor form rather than the liquid form.
So then when it comes out at like 4, is it just like normal steam? Or is it still?
Yeah, it's what we would think of as steam, like steam coming off of a boiling pot usually. Yeah. So it's like superheated steam, which is if it's a very dry steam, meaning it's very, very hot, it doesn't even look like steam. In that it's not like translucent as you're looking through it, it's not foggy, it's just, you can see through it very easily, but it also like scalds all of your skin off if you touched it, so you don't have to get too close to it. So dry vapors are very dangerous, because with steam you can often see it coming out, and with the dry vapor you can't, and so accidents do happen because people walk in front of a leak or something like that. But,
when I was a co-op at a chemical plant,
yes.
anytime it was a big joke that everything we did was very antiquated. And so if they have a power plant just for supplying steam to move the chemical supplies, if there was ever a breach, the policy was to freeze if you were in the area. If not, you were to grab a broom and start doing this in front of any lines. And then when the end of the broom got cut off, they knew that was where the leak was.
That's awesome.
They said they had a whole room full of broken and cut brooms.
Yeah,
just from where the steam sliced it.
So that's like your canary is this broom,
Yeah.
so you don't get sliced. Yeah, it's pretty dangerous when you're working with high pressure stuff, and especially if it's hot and at a very high pressure. It can really be. Okay, any other questions about the setup of this cycle? It should be familiar to you because every single one of these devices is a steady flow engineering device that we've already studied and analyzed. We're just putting them together now in a vapor power cycle to have a network output. And the advantage with a vapor power cycle over a gas turbine is that we have a pump pumping the liquid here. So there's significantly less power that has to be returned to the pump in order to complete the cycle. So in a gas turbine, we have to power a compressor, which requires sometimes half or more of the power that we're generating in order to keep the cycle going. Whereas with a pump, much less of the energy that you create goes back into powering the pump. There are other, positives and negatives to these two, but that's one major one. Okay, so we've kind of gone through all the steps of the cycle, but basically water enters the pump as a saturated liquid. It's pumped up to the boiler pressure. The boiler is where we have some exchange with whatever fuel source we're using. So if it's coal-fired or gas-fired or whatever, a nuclear power plant, then we're receiving heat into the boiler, which evaporates this liquid. That superheated vapor then goes into the turbine, spins the turbine blades. We get a network output, and then the energy, and then the fluid comes out at a lower energy because energy is extracted, which means that it loses a lot of its heat, loses its pressure, and then goes into the condenser to be completely turned into a liquid so that we can pump it back up to the boiler. So this cycle just occurs consistently, constantly, and just generates electricity for us. So we have these 4 steady flow devices, and we can analyze them each individually as their own system, or we can look at the entire Rankine cycle as a whole and analyze it as a system that way. So when you approach your homework, in many cases, you'll have to do both. You'll have to look at each individual system, and then sometimes you look at the overall system to determine, like, for example, the thermal efficiency of the overall system, or if you needed to know the net work output or something like that. So the general form of the energy equation will be applied to each one of these steady flow devices. Q in minus Q out plus work in minus work out minus work in, or flip the signs, is equal to the enthalpy of the exit minus the enthalpy at the inlet. And so this equation can be used to determine any heat and work interactions in each of these steady flow devices. And if we look at them in general, for the ideal Rankine cycle, the pump doesn't lose any heat. Okay, so to make it clear also in your homework, sometimes you're working with an ideal cycle and sometimes you're working with a cycle. If it says it's an ideal cycle, then you know the steady flow devices like the pump and the turbine are isentropic. If it doesn't say ideal and you have an isentropic efficiency, then you know that it's the actual cycle and they're not isentropic.
Please say that again.
Yes. So if it says ideal Rankine cycle, and this goes for any other cycle too, if it says the ideal cycle, the ideal, okay, that means that the pump, the turbine, the compressor will be isentropic. Okay, so if the pump is ideal, then it's not losing any heat, and so the work of the pump can be written as H2 minus H1, or V1 times P2 minus P1. So this is the flow work of a pump. It's the specific volume multiplied by the pressure difference. And this specific volume at state 1 will be approximately the same as the specific volume at state 2. They'll be very, very close to the same value because water is an incompressible substance. So if you're compressing water, the density usually doesn't change very much. So we just approximate it as incompressible. So that's how we determine, in either of those two ways, the work of the pump. And we analyze this H1 and this V1 as the H sub F or the V sub F at whatever the pressure is given at that inlet. And then the boiler, we assume that there's no work going on in the boiler. It's simply just a heat exchanger. So there's a heat interaction, but not a work interaction. So our heat in is just equal to H3 minus H2. The turbine, again, we're assuming it's isentropic. There's no heat interactions with the outside. So the work of the turbine is just H3 minus H4. And in the condenser, we're removing heat from the fluid. It's equal to H4 minus H1. So if we want to look at the total overall thermal efficiency of the whole cycle, it's work net over Q in. So work net is going to be equal to the work of the turbine minus the work of the pump. And that's also equal to Q in minus Q out. And you can see Q in is into the boiler, Q out is out from the condenser. So this should all be familiar and easy. It's what we've done before. Let's work on an example so that we can put it into practice. So in this example, we have a steam power plant operating on the simple ideal Rankine cycle. And it's called the simple ideal Rankine cycle because we're about to get complicated and adding a lot of extras into it, just as we did for the Brayton cycle. We can have reheat, we can have regeneration, we can have cogeneration. So we'll add a lot of that nice stuff in there for you. Simple ideal Rankine cycle, steam enters the turbine at 3 megapascals and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascals. So we want to determine the thermal efficiency of the entire cycle. We know the pressure because the Rankine cycle operates between two distinct pressure limits, the pressure of the condenser and the pressure of the boiler. We know that it's between 75 and 3 megapascals, so 75 kilopascals and 3 megapascals. So to determine the thermal efficiency, what values are we going to need to calculate, or what are we going to look at? What do we need to know from this cycle to figure out its thermal efficiency?
Work net and Q in.
Okay, so work net and Q in, or if we look at the other form of the equation, we might just do Q out and Q in. So we can do it this way or this way, depending on which one is easiest for us to find all the values for. Okay, so let's get started on that. And as we approach these problems, and I highly recommend in your homework that when you're given a problem statement and you have a picture that doesn't have property values on it already, write all the property values down as you're reading the statement so that you make sure you understand, particularly as the systems start to get a little bit more complicated and we have like a reheat or a regenerator in there. Okay, so we have our nice little picture. Let's start looking up properties at the various states. So state 1 is a saturated liquid going into the pump. It's a saturated liquid. We're going to look up H1 and V1, and we don't need entropy. So Okay, so H1 is 384.44 kilojoules per kilogram. V1 is 0.001037 meters cubed per kilogram.
That's at 75 APA.
Yep. So that's state 1. State 3 is also completely specified and it's superheated. So we can look up at 3 megapascals and 350 degrees Celsius, we find H3 is equal to 3116.1 kilojoules per kilogram.
So this is where I'm confused.
Yes.
How do you know what you need to look up? Like, how do you know you need H and V? Like, why not S?
Yeah. Okay, that's a really good question. And so sometimes we don't know at the beginning what we need to look up. So we think, okay, in this problem I need to find the thermal efficiency, which is going to be equal to either work net over Q in or 1 minus Q out over Q in. Okay, so if I look at this entire system, my work net is going to be the work of the turbine minus the work of the pump, right? So work of the turbine minus work of the pump. And I know that like the work of the turbine, I'm going to need to know H4 and H3. And for the work of the pump, I'm going to need to know H1 and H2. Okay, if I opt to do it this other way and instead look up Q out and Q in, I know Q out I'm going to need to know H4 and H1. Q in I'm going to need to know H2 and H3. So eventually you need to look up all the enthalpy values no matter which approach you take to solve for it. So I always start with the states that I know are totally specified, and in this case it's state 1 and state 3 that I can look up all the other property values, and then use those to eventually get all the states specified, which I'll show you in a minute. In this problem, I looked up entropy values. I don't know why, because I didn't fully need them. Oh yeah, you do. You can use them. So yeah, let's look up, and because if we're making the isentropic approximation, then S2 is going to be equal to S1, and S4 is going to be equal to S3. So I did look up entropy values, and in this case for state 1 it's 1.2132 kilojoules per kilogram Kelvin, and state 3 we have S3 is equal to 6.7450 kilojoules per kilogram Kelvin.
So do you not need to know the specific volume in state 3?
I don't need to know the specific volume at state 3. I only need it at state 1 because I'm going to find the work of the pump is equal to V times P2 minus P1. That's the only state I'll need it at. Coincidentally. You can always look them up, and then if you don't need them, that's fine too. But okay, so we know state 1 and we know state 3. And state 2, we know that it's 3 megapascals is the pressure. We know that S2 is equal to S1, so we could use that to find H2. An alternate way to do that would be, I go to the next slide just so I have more room. So the work of the pump is equal to V1 times P2 minus P1, which is also equal to H2 minus H1. So we can say that H2 is equal to V1 times P2 minus P1 plus H1. We know H1, we know P1, we know P2, we know V1. So we can plug all of those numbers in and solve for H2, which I'm not going to write them all down just for lack of time. So 387.47 kilojoules per kilogram is H2.
So then can you just go ahead and plug the rest back in and find the work pump?
Yep. So if I want to find the work of the pump, and I can plug those numbers in, the work of the pump is equal to 3.033 kilojoules per kilogram. I'll need that later. So now we know values at state 2. We found H2 was equal to 387.47 kilojoules per kilogram. We need to find H4. So any ideas on how we would find the enthalpy at state 4?
Use the work of the turbine out.
Okay, do we know the work of the turbine now?
No.
How do we calculate it? Yeah, we need H4 to calculate it, right? So we can't do that, but what do we know about an ideal cycle?
Isentropic.
It's isentropic. So we know that it's 75 kilopascals and that S4 is equal to S3. Okay, so it's 75 kilopascals and S3 equals 6.7450 kilojoules per kilogram Kelvin. What is the state of our substance? How would we find that out?
Superheated.
Okay, so what are we at state 3 coming into a turbine? Ideally, we're always superheated, right? But state 4 coming out, we might still be superheated, but we might be a mixture. Okay, so we have to go to the table and find out if we're a mixture or if it's still superheated.
So even at 75 kilopascals, you're superheated?
You could be superheated depending on the temperature. Because that's sub-atmospheric pressure, so it doesn't take a very high temperature to boil it. Okay, what'd you find there, Kane?
It's saturated liquid making mix because it's in between the HP values for 75 kilopascals.
Okay, so it's in between S sub F and S sub V. It means that we're a saturated liquid vapor mixture, so we can calculate exactly where we are. So X4 will be our quality is S minus S sub F over SFG is 6.7450 minus 1.2132 divided by 6.2426 gives us a quality of 0.886. We could probably round that to 0.89. So then we calculate H4 is equal to H sub F plus X HFG, which is equal to 2402.748 kilojoules per kilogram.
So is the SF just coincidentally the same thing as S1?
Yes.
I mean, it is a time.
It is.
Unless I made a typo.
Both at 75 kVA, so it has to be the same ones. That's why.
Oh, yeah.
That's why it's-
It's by design. Okay. Okay, so now we know H4 is equal to 2402.748 kilojoules per kilogram. So we can calculate our thermal efficiency because we know all of our enthalpies. We can calculate the work of the turbine, the work of the pump, or we can calculate Q out and Q in. Either way we want to do that, we should get the same answer. So let's just do it with work net. So the work of the turbine is equal to H3 minus H4. We plug in the numbers for that. And I didn't calculate it directly. So it's 3116.1 minus 2402.75 is equal to some number. And we minus 3.033, which is the work of the pump that we calculated earlier on the other page. So we find our net work is equal to 7 10.3 kilojoules per kilogram.
Work turbine ounce, 713.35.
Thank you. Then we calculate Q in, and actually this is a lowercase q because we don't know the mass at this point. Q in is equal to H3 minus H2. So we plug in the numbers for that, we get 2728.63 kilojoules per kilogram. So our thermal efficiency is work net over Q in is equal to 710.3 over 2728.63. So we have a thermal efficiency of 26%.
What is that 3.033?
This is the work of the pump.
Oh. Yeah, it is.
So when you did stage 3, I don't know if I asked this yet, but did you look it up based on the temperature or based on the pressure?
Stage 3,
Yeah.
temperature and pressure, because it's superheated. So in table A6, we have all of these columns of pressure, these little categories of pressure. So if I were to go to 3 megapascals, that's far away. So if I go to 3 megapascals on page 909, then I see at 350 degrees Celsius, yep, there's definitely a column there, so I know for sure that I'm superheated. If I went to 3 megapascals and let's say my temperature was like 200 Celsius, and I go here, then I think, oh, there is no 200 Celsius at 3 megapascals. That means I'm actually a compressed liquid, so I have to go to compressed liquid table or make a compressed liquid approximation. So, but by and large, coming into a turbine, you should have a superheated vapor. That's one that you can always pretty well assume is going to be superheated. And then coming out of your condenser, it should always be a saturated liquid or a compressed liquid, in which case you just make the saturated liquid approximations coming out of the condenser. So those two states are fairly well specified. Coming into the boiler would be a compressed liquid, and coming out of the turbine can be a superheated vapor, saturated vapor, or a saturated liquid vapor mixture. Yes, right? So if you think about the cycle, here it's liquid coming through this condenser into the pump. It's still liquid, then it gets to the boiler, it gets evaporated, so it's superheated. And as it goes through the turbine and loses energy, then it is starting to condense, but it's condensed further once you get to the condenser. Does that make sense? Any other questions about that? Are you okay, Blake?
I'm just thinking how
He's
much
very quiet.
make up a 58.
Okay. Let's do another example. This is very similar to the one that we did before with a power plant. So now we're looking at it not just as the Rankine cycle, but it's a power plant that's operating on the Rankine cycle. And there's additional information that we need to find this time. So we want to find the thermal efficiency of the whole cycle, but now we're trying to find the mass flow rate of the water and the temperature rise of the cooling water. Okay, so we have a net power output of 45 megawatts. Steam enters the turbine at 7 megapascals and 500 degrees C, and is cooled in the condenser at a pressure of 10 kilopascals by running cooling water from a lake through the tubes of the condenser at a rate of 2,000 kilograms per second. So m dot of the cooling water in the condenser is 2,000 kilograms per second. So we want to show the cycle on a TS diagram and determine the thermal efficiency, the mass flow rate of the steam, and the temperature rise of the cooling water. Okay, so this is very similar to what we did before. There's just additional things that we're now trying to figure out, because in the condenser, we're going to find Q out, but then we also need to compare it to the temperature change of whatever's receiving that water, which we can do. It's fine, because we can do an energy balance in the condenser as a heat exchanger. Okay, so at state 1, it's 10 kilopascals, and we make the compressed liquid approximation to start looking up the properties at state 1. I'm just going to do this on the next slide. So state 1, we know that it's at 18 kilopascals. No, 10 kilopascals.
Take me.
Yeah, 10 kilopascals is 7 megapascals. Okay. So 10 kilopascals, we know that H1 is 191.81 kilojoules per kilogram. V1 is 0.001010 meters cubed per kilogram. And S1 is 0.6492 kilojoules per kilogram Kelvin. State 2 is a compressed liquid. Okay, so that's after the pump. But we know that the pump is isentropic, so S2 is equal to S1, which is 0.6492. We also know that V2 is approximately equal to V1 because water is incompressible. So we can find the work from 1 to 2 is just V times P2 minus P1. And P2 is 5 megapascals. So this work from 1 to 2, if we take specific volume 1, multiply by P2 minus P1, we calculate that to be 7.06 kilojoules per kilogram.
How did you find P2?
P2 is given in the problem, it's 5 megapascals. Oh no, 7 megapascals. My memory is poor. 7. Yeah, there it is. Okay. 7 megapascals, or 7,000 kilopascals. Okay, so we calculate the work from 1 to 2 using P2 and P1. Then we can solve for H2 if needed. H2 is equal to H1 plus the work from 1 to 2. So we find H2 is 198.87 kilojoules per kilogram. State 3 is a superheated vapor going into the turbine, and it's specified as P3 is 7,000 kilopascals, T3 is 500 degrees C. So we go to table A6, we look that up directly, we can find H3 and S3 is 341.4 kilojoules per kilogram, and S3 is 6.8000 kilojoules per kilogram. In state 4, we know that the pressure at state 4 is equal to 10 kilopascals, because there's only 2 pressures in a Rankine cycle, pressure of the condenser, pressure of the boiler. So the pump and the condenser are at the pressure of the condenser, and the inlet of the turbine and the boiler are at the pressure of the boiler. Okay, so P4 is 10 kilopascals, and we know that S4 is equal to S3 because the turbine is isentropic. So we find S is equal to 6.8000 kilojoules per kilogram Kelvin, which if we look this up at 10 kilopascals, and that's an entropy value, we can see that it's a saturated liquid vapor mixture. So we can calculate our quality is S minus S sub F over SFG. This is S4. We plug in the numbers for that using the values at 10 kilopascals, we get 0.82. So then we can find H4 is equal to H sub F plus X HFG, And using again the values from 10 kilopascals, we solve for H4 is 2153.33 kilojoules per kilogram. Okay, so just by following from state 1 to 2, 2 to 3, 3 to 4, I can fully specify all the inlets and outlets of all these steady flow engineering devices. So once I have all of these values and all of these numbers, then I can analyze the system in many different ways and do what I need with it. Yes.
So how do you know for state 4 to calculate the quality, like instead of anywhere else?
Because when I looked at this entropy value and this pressure, I see that for 10 kilopascals, I'm in between S sub F and S sub G on that table. So in order to figure out exactly where I am, I have to calculate the quality. Yes?
How do you know that P3 equals P2? Is that from the diagram?
Yes. So if we look again at the Rankine cycle, this pressure here, before we go into the pump, is going to be the same as this pressure here at state 4. If we also look at the property diagram here. So these are lines of constant pressure, and this is just how the Rankine cycle operates, that it's between two lines of constant pressure with an isentropic process taking you from one pressure to another. So the ideal Rankine cycle will always just be a low pressure condenser and a high pressure boiler. So the pressure at the exit of the boiler is going to be a high pressure, and the pressure at the exit of the pump is also going to be that high pressure. Whereas the pressure at the exit of the turbine and the entrance of the pump will be at the low pressure. Yes?
That's only for ideal, right?
Well, for the ideal and the actual cycles, we generally just operate between two pressures. If you want to be really particular in analyzing them, then you assume the pressure will change also in addition to some of the other pressure. We're going to do an example of the actual cycle in a minute. But that significantly complicates things, and you have to do a numerical analysis rather than using property tables. So for this class, we just always still assume that the pressures are consistent. Where it will change is when we start going into like a reheat and regenerate cycle, that there's going to be more than two pressures involved.
The PV diagram, that's the one that's the square, so you know it's pressure constant, right?
No, the PV diagram is not a square. That was for the Carnot cycle.
Oh.
Yeah, it won't be square. At least, pause on that step. Okay, so we've got all of our states specified, states 1 through 4. So now we can start calculating some of the information that we want in this problem. So part A, we want to know the thermal efficiency of the entire cycle, which is just the work net out over Q in, and in this case it's the work net out is the work of the turbine minus the work of the pump over Q in. And we don't have a mass flow rate of our steam flowing through, so it's okay to use these in lowercase. So the work of the turbine is going to be H3 minus H4, and the work of the pump we calculated previously here, this work 1 to 2, which was 7.06 kilojoules per kilogram. So this is V1 times P2 minus P1. And then Q in is going to be equal to the Q that comes in from states 2 to 3. So it's H3 minus H2. H3 minus H2. So if we plug in all the numbers for that, we find our thermal efficiency is equal to 38.9%. so then part B, the mass flow rate of the steam. So we're given in this problem the mass flow rate of the cooling water, which is flowing through this condenser here. So from state 4 to 1, we know that there's some cooling water that's being used in order to condense the steam as it flows through. So it's just like a heat exchanger, basically, where we can consider that the water is coming in from state 4 to state 1 in our condenser, and then we have our cooling water in and our cooling water out. So we're given the m dot of this cooling water is equal to
2,000 kilograms per second.
okay, kilograms per second. So we know that the heat that's being removed from the steam is going into the cooling water. So we can say Q out of the steam is equal to Q in of the cooling water. Or we can say m dot of the steam times H4 minus H1 is equal to m dot of the cooling water times C sub P times this delta T of the cooling water. Okay, so we need to find this increase in temperature of the cooling water. We also need to find the mass flow rate of steam. And I think I missed a page from this.
Should we have found the mass flow rate of the steam first from the output of the
Yeah.
turbine?
Yep. Okay, so the mass flow rate of the steam, we'll have to solve for it using what we know about the turbine. So we know that the work dot of the turbine is equal to 45 megawatts, which is equal to m dot of the steam times H4 minus H1, right? So then we use that to solve for m dot of the steam is equal to 35.97 kilograms per second. So we can plug that back into this equation up here, and we can solve for this delta T, which is here. So we know H4, we know H1, we know this m dot of the steam. This wouldn't be H4, H1. It would be H3H4. Sorry. Because it's, that one would be H3H4. Jeez. Okay, hold on. Oh no. Now what I do? Just do it?
Yeah, Tony Calibrate.
Can you say the lots, please?
Finish the race.
Okay. I don't like this thing anymore. I liked it at the beginning of the semester, now I don't. Okay. I gotta have my picture in front of me, it's a problem. Okay, so the mass flow rate of the steam is through the condenser, that's H4 minus H1. That one is correct. But the mass flow rate of the steam through the turbine is H3 minus H4. Okay. So make sure you correct that in your notes. Okay, so we solved for the mass flow rate of the steam. Plug that back into this equation, we can solve for this delta T, which is equal to 8.4 degrees Celsius. Okay, so we have our thermal efficiency, we have our mass flow rate, and we have our delta T. Okay, any questions on this example?
So when you're finding the delta T,
Yes.
do you initially convert it to Kelvin?
When you're finding a delta T, it's the same in Celsius as it is in Kelvin, which that was an issue on some people for the homework because it was talking about a temperature rise of 25 degrees C above something else on one of the homework, I think homework number 3 or 4. So a delta T in degrees Celsius is not multiplied or added to 298. So if you're increasing by 25 degrees Celsius, you're also increasing by 25 Kelvin. So you don't convert that delta T by adding 298 to it. So a lot of people had very wrong temperatures in that particular problem. So that anytime you're finding a delta T, you don't have to make that conversion because the spacing between degrees in Kelvin and Celsius is the same. It's just the slope of the line has a different intercept. Okay. All right, so heat rate is another way that we talk about the conversion efficiency of a power plant. So it's the amount of heat that we supply to it in BTUs that is converted to kilowatt hours. So it's another way of measuring thermal efficiency if you're comparing plants like a coal-fired plant versus a natural gas plant. Knowing the heat rate is more important than knowing necessarily thermal efficiency based on Q in and work net. So it's just an alternate way of looking at it. And you can convert between BTUs and kilowatt hours using that conversion there. Okay, so deviation from ideal. So we've talked about the ideal cycle thus far and how we use it and how we analyze it. But in reality, the turbine and the pump are not going to be isentropic. They'll have irreversibilities associated with them. So there's fluid friction, there's head losses, there's heat losses from either of those devices, and then there may be additional things that cause them to be less than perfect, like if the pump is imbalanced or has too much vibration, or the same for the turbine, or if the fittings are not very tight and there's steam leakage out the gaskets, things like that will reduce the efficiency of each individual device, and cumulatively it reduces the overall efficiency of the cycle. So we have this ideal version of the Rankine cycle in mind that we can analyze and use as the base model. However, in actuality, it operates slightly differently. So this goes to your question, Chris, about pressures, that in actuality, we're not going to have, Taylor's,
He may be.
It was a bold request.
okay,
I told her something.
okay, whoever asked it, someone in the back row. So in actuality, you'll have some pressure drop as your components of the system have friction within them. So anytime you have water traveling through a pipe, there's going to be some pressure loss, and there's a pressure drop in the boiler. So it will not follow that perfect, lovely pattern. So we still analyze it and try to encapsulate the issues that happen in the turbine and the pump, but we don't necessarily look at all the pressure drops throughout the whole system because that significantly complicates the analysis. So we still are going to imagine that we're operating on lines of constant pressure, but now instead of following this perfectly straight isentropic line, in actuality, we're operating such that we increase entropy as the steam flows through the turbine. And in this case, as we compress our liquid in the pump, we also increase entropy. So the actual case will be isentropic, meaning that we won't have any irreversibilities, we won't generate any entropy. However, we actually do. So entropy is always increasing in the actual versus the ideal. So how do we measure that? Well, we've talked previously about isentropic efficiencies, and so for pumps and for turbines, we know that we can compare the isentropic work to the actual work, which if we expand those out, it's H2 isentropic minus H1 divided by H2 actual minus H1. So in many cases, what we do is we analyze the system as if it were ideal. So we find our isentropic enthalpy. Then if we know the isentropic efficiency of the device, it's easy to apply that and calculate what our actual enthalpy will be. And we'll go through and make examples of that. So we do that for both pumps and turbines. But you notice that in the case of the pump, that the actual work is in the denominator, whereas for the case of the turbine, the actual work is in the numerator. And that is because the actual work for a turbine is going to be a smaller value than the isentropic work. We can't have an efficiency greater than 1. Whereas for the pump, our actual value for work is going to be higher than the isentropic case, meaning that our pump has to consume more work or more energy in order to do the same thing, to exact the same amount of pressure change. Whereas our turbine will get less work output of it because of irreversibilities in the system. So let's do another example. And in this case, it's a steam power plant again, operating on the cycle shown above. So we are taking into account the pressure drops throughout here, that we're not operating on these nice, neat little lines. If you're not given that information about specifically what pressure, how the pressure is changing, you can't analyze it. But because we're given all those distinct pressures, we can. So we have a lot of different states to analyze. We have now 6 states rather than 4, as we did before. We have our isentropic states and our actual states, so we have to look at it that way. So if our pump is 85% efficient and our turbine is 87% efficient, we want to determine the thermal efficiency, the overall thermal efficiency of the cycle, and the net power output. So we're given a mass flow rate of 15 kilograms per second, and all the properties are given to us on the diagram that will allow us in order to perform that analysis. So if we want to calculate the overall thermal efficiency, again, is work net over Q in. So we'll probably need to figure out the work of the pump and the work of the turbine, and then we're going to need to see how much Q is coming into the system in the boiler. So let's take a look at that. So at state 1, at 9 kilopascals and 38 degrees Celsius, we find S1 is 0.5445 kilojoules per kilogram Kelvin. V1 is equal to 0.001007 meters cubed per kilogram. State 2 isentropic, we know that S2 is equal to S1. State 3, we're given 15.9 megapascals and 35 degrees C. We can also look up everything at that state. So H3 is 160.8 kilojoules per kilogram. Similarly, coming out of the boiler is fully specified, so we can look up H4 at superheated state is 364.5 kilojoules per kilogram. And state 5 is fully specified. H5 is 3581 kilojoules per kilogram. And S5, because we'll need that to figure out state 6, S5 is equal to 6.677 kilojoules per kilogram Kelvin. So the only state that we aren't able to look up property values are states 2 and state 6, but we can figure them out. So if S2 is equal to S1, we can look in the property tables and we can figure out for state 2 that H2 is equal to 175.2 kilojoules per kilogram. And then at state 6, if S5 is equal to S6 is equal to S5, then similarly we can go to the tables and we can find our H6 is equal to 2114 kilojoules per kilogram.
So like from 4 to 5, we're just somehow losing pressure.
Yeah, because it's going through some pipes, and the pipes are losing pressure. So in this problem, all of the pressure values are given to you and it's fully specified. There's no way to calculate that unless you have very detailed information about the pipe or you're measuring it at different points along your system. So in general, your homework problems are not going to have these changing pressures and things, but you will have to account for isentropic inefficiencies in pumps and turbines. So don't get too caught up on pressure changes in the pipes, but worry more about how to figure out isentropic efficiencies or how to find actual property values when you're given the isentropic efficiency. So we can figure out our pump work, so the work of the pump is equal to V1 times P2 minus P1. So P2 is 16 megapascals, P1 is 9 kilopascals. We looked up V1 in the table, so we find that that is 161 kilojoules per kilogram. Okay, now this is the isentropic work of the pump. So the actual work of the pump is equal to the work of the pump divided by the isentropic efficiency of the pump. So it's 161 divided by 0.85. So the actual pump work is actually this is 16.1, is 18.95 kilojoules per kilogram. Similarly, for the work of the turbine is equal to H5 minus H6S. So we plug in the numbers for that. We looked up H5 and we found H6S, so the isentropic state. So we calculate that to be 1467 kilojoules per kilogram. But the actual turbine work is going to be equal to this work of the turbine multiplied by the turbine isentropic efficiency. So it's 1467 multiplied by 0.87, which gives us 1276.29 kilojoules per kilogram. So we have our pump work, our turbine work. We just need to find the heat into the boiler. So Q in is equal to H4 minus H3, which it is 3484.2 kilojoules per kilogram. So now we know our pump work, our turbine work, and our Q in. We can plug it back into this equation for thermal efficiency. And we calculate that to be 36.1%. We also want to know the work, the net power out. So what we found was work net is equal to the work of the turbine minus the work of the pump. W dot net is going to be equal to M dot times this work net. And our M dot is given to us in this problem, 15 kilograms per second. We plug that in and we find our work net is equal to 18.9 megawatts. Okay, so again, these problems, they're all very similar. You just have to figure out what you know about the system already and try to define those states. Then you look for clues as to how to find the other states. So if something is isentropic, or if it tells you it's the same pressure, or isothermal, whatever it might be, then you find and you just kind of step through and find and specify all of the states using that same methodology. And then if you know isentropic efficiencies, or you have to calculate them, then you just should be able to understand that isentropic means the entropy doesn't change from the inlet to the outlet.
So for the H, like, 6, I guess, S, like, what's the difference between that and H6A?
So H6S is here. So we're going from 5 to 6 isentropically. But in actuality, it's not an isentropic process, so the entropy increases a little, and this enthalpy value is going to be further along that line. So your enthalpy at the exit is actually going to be higher than it would be in the isentropic process.
So what's different about looking those up? Like,
Well, you have to have two independent variables to look up the state, right? So at this state, you know the pressure is 10 kilopascals, but you need a second variable in order to fix the state. And in this case, you say, okay, I have entropy, because I know the entropy doesn't change. So now I know the pressure and the entropy. I can go to the table and look it up for state 6. But it's the isentropic version of state 6. because I know the isentropic efficiency, I can use that to calculate the actual enthalpy at state 6. And in this case, I didn't calculate it explicitly, I just calculated the isentropic work of the turbine and then multiplied it by the efficiency to figure out what the actual work would be.
So when you say like, you can calculate to find the actual, what's that method?
So the efficiency of a turbine is equal to, in this case, it would be H5 minus H6 S over H5 minus H6. I might have this flipped. Let's see. The actual is going to be larger. This one's going to be actual. This one's going to be S. So you know H5, you know H6S, you know the isentropic efficiency, you solve for H6 actual.
Okay. So you do that, so like what if like you're not given the efficiency?
You either have to be given the efficiency or you have to be given the actual state.
Okay.
Because you can't fix the state otherwise. If there's too many, and that was what happened actually on your homework problem, one that I set up. I started solving it and there were too many unknowns, so I had to give you one more property value so that you could solve it without having to guess and then go back and forth. Okay, so let's just real quickly talk about some things that we can do. And actually this is there in your notes if you are interested. I haven't yet checked to see if the computers upstairs have ease on them. They're supposed to. Has anybody looked at that? I think we're going to start trying to use it, assuming that it's up there, because I think it's actually pretty fun and easy to use, and it makes the homework a lot easier if you use these. Okay. So we can increase the efficiency a couple of different ways. One is to lower the condenser pressure. So the advantage of doing that is that it automatically lowers the temperature at the output of the turbine. So it gives us this net increase in work. However, if we lower the pressure too much, then we can have seepage into the condenser from the outside air because it's subatmospheric. And then also if the condenser pressure is too low, then too much liquid condenses in the turbine, which can cause pitting and other things that we don't want. Superheating the steam also serves to increase the net work, but we can only do it so far because we can go beyond the metallurgical constraints of the system, so meaning that we're going to start working on turbine because it's too hot, or we're not able to contain this high pressure, high temperature steam, and we start cutting people's broomsticks off. So it decreases moisture output at the turbine exit, but it's not always easy to do, and we're limited by the fuel sources that we have as well. And so increasing the boiler pressure is another option, but again, it comes with possibility of dire consequences if that boiler pressure is too high and it ends up failing. And then it again leads to increased moisture in the turbine at the exit, because as we increase the boiler pressure, then our state 4 at the exit slides over a little bit. So it can cause problems too. So all of these things are ways to improve, but we have to balance our improvements with any disadvantages that we add to our system or cost increases, as always in design and engineering.